This is Advanced Algebra Lesson 6-9, Complex Numbers. As we discussed in Lesson 8, we introduced the whole concept of an imaginary number, a pure imaginary number. And a pure imaginary number fits under the umbrella of complex numbers. Complex numbers are numbers of the form a plus bi, where I is equal to the square root of -1, and are operated with as if they are polynomials in I. So let's take a look at what a complex number is. A complex number is a number in the form of a plus bi, where a and b are real numbers, and I is equal to the square root of -1. We consider a to be the real part, and b is the imaginary part. For example, 4 plus 3i. 4 is the real part, and 3 is the imaginary part. Not 3i, but just 3. For complex numbers to be equal, both the real and the imaginary parts must be equal. So let's take a look at some of the properties that we have with complex numbers, and we'll call it the properties of complex numbers postulate. In the set of complex numbers, addition and multiplication are commutative and associative. Multiplication distributes over addition and subtraction. 0 is the same as 0i, which is also the same as 0 plus 0i. That's the identity, the additive identity, and 1 is equal to 1 plus 0i is the multiplicative identity. Every complex number a plus bi has an additive inverse of the opposite of a plus the opposite of bi, and a multiplicative inverse of 1 over a plus bi, provided that a plus bi is not equal to 0. And the addition and multiplication properties of equality hold. So let's take a look at our first example here. We're going to look at 7i times 9 minus 6i, and we're going to put that in a plus bi form. So we need to distribute our 7i, that becomes 63i, minus 42 times I squared. And we know from our previous lesson that I squared is the same as -1, so we have 63i minus 42 times a -1. So that would give us a positive 43 plus 63i if we were going to be in a plus bi form. Remember, this is the real and this is the imaginary part. When we look at example 2, we want to multiply and simplify. So we want to distribute our 5 through the 6 minus 2i. So that would be 30 minus 10i, and then we're going to distribute the 7i. So 7i times 6 is 42i, and that would give us a negative 14i squared. We know that I squared is a -1, so let's go ahead and simplify what we can. 30 and a positive 14 would make 44 plus 32i. Now, we're going to introduce a term called complex conjugates. When I say complex conjugate, I always think of a grammar lesson. We're going to look at it in terms of mathematics. So a plus bi and a minus bi are considered to be complex conjugates of each other. The product of complex conjugates always is a real number, and that's very important when we are dividing complex numbers. I'll show you what we mean in example 3. We have some rules, and one of the rules is we don't have an I in our denominator. So we need to get rid of this 3 plus 4i down here. We don't want to have that. We want to simplify that. So we want to multiply the numerator and denominator by something that's going to give us to get rid of this. And we know that if we multiply by a complex conjugate, we'll get a real number down there. So if I'm strategic in multiplying, if I know that I can multiply by 1 and it doesn't change my value, so because that's the multiplicative identity. So if I multiply by something that looks like a 1, 3 minus 4i over 3 minus 4i, I'm not changing the value, I'm just going to change its appearance. So you can see I have the math worked out here. I took and multiplied 3 minus 4i by the numerator and the denominator. So when I go ahead and multiply that through, that gives me 15 minus 20i minus 6i plus 8i squared. And then on the bottom I would get 9 minus 12i plus 12i, and then minus 16i squared. So when we do that, when we multiply by the complex conjugate, this middle term goes away, and because we're multiplying by a -1 here, we know that's -1, our i's are going to disappear as well. So on the bottom, 9 minus a positive 16, I'm sorry, that would become 9 plus a positive 16. That would give me 25. Let's simplify on top. This would give me a -26i. This would be a -8. So 15 and a -8 would make 7. So that gives me 7 minus 26i over 25. But they asked me, or they have been talking about things in a plus bi form. So we want to move this into a plus bi form. So that'd be 7 over 25 minus 26 over 25i. So now we have our simplified form of 5 minus 2i over 3 plus 4i, and our answer is now in a plus bi form. Since we introduced complex numbers, I'd like to take a look and see how that fits into our hierarchy of numbers that we have now studied up until this point. First of all, because a plus 0i is the same as I, every real number is a complex number. So the set of real numbers is a subset of a complex number. So as you can see here, if we have complex numbers at the top, it branches out into real numbers and then continues down with everything that we had studied up until this point. So this was everything that you knew up until this chapter. But now that we've added the complex numbers, we've added a whole nother branch, and that's our pure imaginary numbers, bi. It equals 0 plus bi. So the set of pure imaginary numbers is also a set of the set of complex numbers. So we can see over here, a plus bi, b can't equal 0. And then we have pure imaginary numbers where it's just 0 plus bi, and assuming b is not equal to 0. Let's take a look at an application of complex numbers. In your reading, it talked about parallel circuits, and it gave you a formula: z sub t equals z sub 1 times z sub 2 all over z sub 1 plus z sub 2 to find total impedance. So in example 4, find the total impedance in a parallel circuit if Z1 is equal to 1 plus I ohms and Z2 is equal to 2 minus 6 I ohms. So we're going to go ahead and insert that into our formula. So that will look as follows: 1 plus I times 2 minus 6I over 1 plus I plus 2 minus 6I. Let's simplify on the bottom. That one's the easiest. 1 plus 2 is 3. A negative 6i and a positive I is going to be a negative 5i. Multiplying above, 2 minus 6i plus 2i minus 6i squared. And if we simplify that, this is going to give me a minus 4i, and this is going to give me a positive 8 all over 3 minus 5i. And we know that we can't have 3 minus 5i in the denominator, so we're going to multiply by the complex conjugate, which would be 3 plus 5i on both the numerator and denominator. So that multiplies out to 24 minus 40i minus 12i minus 20i squared. Bottom would be 9 plus 15i minus 15i minus 25i squared. We know the beauty of multiplying by a complex conjugate is that it gets rid of my i's. So 9 minus 25 times a negative 1 would give me 34. If I simplify up above, that gives me 44 plus 28i. And then if I want to, I can leave it in this form, or if I want it to be in a plus bi form, I would then get 44 over 34 plus 28i over 34. And yes, that can simplify, but we're not going to focus on that at this point in time. We will work more on that as we progress through this course. This concludes Lesson 6-9.